let's go over homework number 4. Please make sure that you understand everything super clear here, okay? Because you kind of have to think about the final exam from this point. So for the first question, review the concept of application of QFD and discuss which of the areas from Deming's system of profound knowledge can be related to the QFD and how. So your answer may vary, okay? This is my answer. So whatever argument you're trying to make, it has to make sense. Okay, so if you think about the Deming's system of profound knowledge is mentioning 4 elements there, okay? The appreciation of a system, okay? Understanding the variation, and the knowledge, and last item is psychology, okay? You need to understand psychology. You need to understand how human mind function. Okay, so question number 2. Okay, maybe I didn't finish this part. So I thought that the QFD is neat because it bring different people, different background, different expertise together to come up with an optimized plan of improvement. Okay, so from that perspective, I can say that QFD can be linked to the system perspective, okay, instead of a siloed perspective or approach. So question number 2, a battery manufacturer makes battery with a 310 milliamp per hour of capacity on average. So in this case, we're assuming that average is known as 310, okay, with a standard deviation of 13. Okay, a potential client has approached and was hoping to see if the machine can be used to satisfy a spec of this. Okay, so before you solve this type of problem, it's always going to be helpful to draw the distribution first. So here is the center, 310. Your client is asking if you can do 339 upper, 261 lower. Okay, so we'd like to know whether we are going to make too many defects that are bigger than or less than the specification limit. So let's figure out the CPK first. So we can take 2 different approaches. One is CPK of upper. In this case, we're seeing 339 minus 310. 3 multiply 13, right? So the lower part is going to be 310 minus 261, 13. So it's going to be whichever that is smaller that is going to be considered as our process capability index. So it's going to be 29, 39, right? This guy here is going to be 49, 39. So even without finalizing the calculation, you can already see this guy here is going to be less than 1, right? 29 over 39 is going to be what? It's going to be 0.7 for 36. Okay, the other one here, it's 49. So this will be 1.2564. So the lower of 2 is going to be considered as capability index 7436, which indicates that this process is not capable of meeting the specification limit that your customer is looking for. And what is the DPMO? Okay, what is DPMO? DPMO, which is a proportion of defect multiplied by 1 million. Okay, 1 million. So we need to figure out what is the proportion here, what is the proportion here by using Excel formula. Lower part, upper part. Okay, lower part is going to be relatively simple. It will be norm dist 261, average is 310, standard deviation is 13. Last one is true. The upper part is going to be 1 minus norm dist 9, 310, standard deviation is 13. Under true here. Okay, so in combination, proportion of defect is sum. Okay, here is going to be the proportion of defect. Let me write it down. 1 to 9 multiplied by 1 million DPMO. So this is your DPMO, 12930. Okay, so if you look at this result and the Cpk, they are agreeing with each other. So as you can see that it doesn't generate a whole lot of defects in the lower part, because the lower part capability index is larger than one, okay? But the upper part, in the upper part, it doesn't do very well. So as you can see, the upper part capability index is actually less than 1. So once you're done with your calculation, make sure that you observe whether these two results are agreeing with each other. Okay, let's take a look. Next. A machine can be adjusted to change its mean capacity to whatever value in 20,000 single time cost. Changing the standard deviation requires huge upfront cost. It usually means you have to refine your machine, okay? That is what it is. Therefore, they are not considering the option at this time. The client is wishing to place a single time order of 25,000 units of battery. Each unit is expected to return $1 in profit. Each defective unit will cost the manufacturer $0.5. So first, please evaluate the feasibility. Is it possible for firm to meet the specification limit without generating too much defects with a mean process adjustment? So if you look at the specification limit, right? 261 here and 339 here. Whatever average it is going to be, whatever average that it is going to be, we need to have at least 3 standard deviation here. Okay, if you can adjust your machine so that you can have at least 3 standard deviation on both sides, and then that will be doable. Okay, of course, economically it has to be justified. So what is this average is going to be? Okay, what is this average going to be? So it's implying that if you spend $20,000, you can bring the average to whatever value you want. So in this case, let's see, we need to have a center point here. Okay, we need to have a center point, 339 minus 261. Okay, so what is here? So this difference here is 78 in terms of the measurement unit. So the entire span here between the lower and the upper, you have 78. Okay, but can we contain 6 sigma within the 78 range? So to do so, I think it's exactly 13 as provided in the problem description. I did not make the calculation more complicated, right? So with that, I think we are feasible. This process is feasible to meet the specification limit without generating too many defects. Okay, as long as your average is put right in the middle. So let me see what the middle is. The middle here means 300. Oops, 300. So in that case, you have a 39 here, 13, 13, 13, 13, 13, 13. So to answer the first question, please evaluate the feasibility. So if you're willing to spend $20,000, this machine, this process is capable of meeting the specification limit. So what is best possible CPK? So best CPK, just by looking at the visualization, is going to be 1, because we are containing how many standard deviation? We're containing, exactly 3 standard deviation, both upper and the lower end. 3 standard deviation. Also for the lower part, 61, 3 multiplied 13, these are exactly the same result as 1. Okay? So the best possible CPK is 1, right? What is the DPMO? DPMO, you can run the calculation here. Like what you can do here is norm dist in Excel, 261 and 313, true. You're going to multiply it by 2, because this area and this area is going to be exactly the same. Okay, so I think that will give you 261, 313, true, multiply 2. It's going to give you 0.0269998. So if you want to get the DPMO, it's going to be this multiplied by 1 million. Okay, so I think you can run the calculation here, so you can do it yourself. Okay. Second, can it meaning the adjustment, be justified financially? Meaning that is it worth spending money to make the adjustment, given the amount of money you'll be making out of this deal? Okay, you kind of have to compare what is the gain and what is loss by making the adjustment. Okay. So conceptually, you are making 25,000 unit plus, I'm not going to use alpha, but you need to use plus maybe, let's say additional. What is this additional? Right? Because to make 25,000 unit, you are always going to generate some defective items in the process. Okay, so 25,000 is the amount of units that you are going to deliver to the customer, and this additional means the defects that's being generated during the process. So in other words, if you use a different color, so I think $25,000 unit is going to be something that belongs to here, right? You also need to think of how many defects will be generated during the process. Okay, so that is simply, you can do non-defect versus defect. These are in terms of count. Okay, so you know the non-defect is going to be 25,000. Let's say the defect is X. We don't know exactly how many are these going to be, but we do know the proportion of defect is going to be 0.0269998, and the non-defect proportion is 1 minus 0.0269998. Okay, so this is solvable. You can solve this, and that will give you the number of x, right? So let's take a look. So my calculation tells me the x is roughly 67, 7, 6. You're roughly generating 68 defects during the process. So you'll be making $25,000, right? You're making $25,000, and because each unit will give you $1 profit, right? Each defect unit will cost the manufacturer $0.5. So you subtract 68, multiply 0.5. You also need to subtract amount of cost that went in to adjust the machine. Okay? So if you do this calculation, I think this is in fact larger than 0. So it depends on how you look at it. If you say, hey, I don't want to go through that hassle just to make about $5,000 profit. I'm sorry. Yeah, it's $5,000 profit. I think exactly it's going to be minus 20,000 minus 34. So we'll be making 4,966. Okay, this is going to be the profit you're looking at. So say, hey, I don't want to go through the hassle to make $5,000. If that is your opinion, you can say, I don't want to do that, okay? But if you say anything that is larger than 0, it's acceptable to me. And you can say this is a deal that I'd like to accept. So this is somewhat subjective, but the key is that you need to be able to demonstrate this process. Okay, so key here is to understand the distribution and how would you like to utilize the distribution to figure out this part of the calculation. Okay, this part of the calculation. So with that, let's move on to number 3. Specification for the lengths of an auto part in Adams Fabricating is 15 plus minus 1.75. Okay, it costs $56 to scrap a part. So meaning that when something went beyond the specification limit, it's going to cost $56. Then K, and determine the expected loss if the process mean is found to be 15.03. So we need to get the K first, right? So it's going to be the deviation. So your deviation here in this case is 1.75 squared. So what is the value of K? Okay. I think it's going to be 18. 2,857. So with this K provided, then you can obtain the potential loss here, the expected loss of the system. It's going to be K D square process sigma square. 18,2,857 multiply what is the deviation? Okay, so the deviation square is the difference between the expected process average and the target. Square. The variance is 49. So if you solve that, your expected loss out of this process is this amount. Okay, it's going to be this amount. And lastly, let's take a look at the number 4. Let's figure out what is the shape of distribution for each process first by plotting a histogram. Okay. So it looks like you don't need to perfect this histogram here, because the purpose of plotting it is just to look at the general shape of the distribution. The machine A looks more like a flat. Okay, therefore we can actually consider this as a uniform distribution. We don't actually need a histogram after looking at the shape. For this guy, this more resembles a normal curve. So the process B follows a normal distribution. The reason why the shape of distribution is important is that depends on the shape, you have different way of obtaining its average and the standard deviation. Okay, so the first question is asking, please analyze each column of data separately. Please construct histogram for each column to discuss what is mean, standard deviation, and the shape of the distribution. Okay, so for mean, standard, just say SD, and the shape. Okay, and here we have machine A and machine B here. So because this is because B is normally distributed, this is uniform distributed. For B, it's fairly simple. You can just say average, right? Our standard deviation is STDB sample B to B. Okay, and for the machine A, we have a slightly different way of calculating it because it's following a uniform distribution. Okay, so what I'm going to do here is 0.5 multiply the maximum minus minimum. Max of A, min of A. Yeah, I don't think this formula is correct here. I think it's plus instead of minus. Okay, and the standard deviation is the square root of the variance here. 12 multiply, again, max of A, min of A, square. Here, okay, standard deviation. So you'll be wondering what happens if we calculate the way we calculate the machine B for machine A. Okay, and then okay, so it's slightly off. It's slightly different. There is a property that is associated with average. So sometimes if you go deep with the statistics, we talk about the bias of an estimator. So meaning that in a certain way of calculating the average and standard deviation, we say underestimating and overestimating. So the reason why we're calculating the average for machine A using this fashion is because we try to avoid this biasness problem. Okay, we don't like to systematically underestimating or overestimating the process mean by using different way of calculating the average. Okay, so if once you determine this is actually the uniform distribution, we'd like to stick to the formula to calculate its average and standard deviation. Although it's not that hugely different, okay, it's not hugely different, but we'd like to be more rigorous in terms of, finding out those parameters. So that will solve the first problem, okay, histogram for and shape of the distribution. What is DPMO if the sample results are very good representation of the actual working condition? So for one of the machine that assumes the normal distribution, please identify the CPK. So you can identify CPK for the machine B here in this case. Okay, you can also identify machine A, but all the example we've been using is based on a normal distribution, so I don't like you to confuse. So I just like you to stick to the machine B in terms of looking for the capability index. Okay, so CPU, CPL. Let's see. So here is our specification limit. I'd like to indicate that here somewhere. They share common spec limit. I think it's lower, not upper. Yes. Okay, so that applies to this as well. So for the lower part capability, it's going to be average minus 3 multiply standard deviation. Okay, so it looks like lower part is doing fine. Looks is also doing fine for the upper. So the minimum of 2 is 1.01. So machine B is doing very well. Okay, and the first question is asking the DPMO. So for that reason, we need to know what is the proportion outside of the specification limit. Okay, if it's a normal, we can find out, right, what is the outside probability. What is the probability that is going to be less than the lower spec and greater than the upper spec limit. So we can get the DPMO fairly quickly. Proportion, defect, too small, too big, right? We do DPMO eventually. So for this guy here, too small is going to be norm dist, lower spec, average, standard deviation. We'll expect very small proportion there. 1 minus dist. The x is going to be upper spec, right? Average is, standard deviation is true. So your DPMO. Okay, so for the machine A though, the reason why it says the DPMO, the sample results are very good representation of the actual working condition. So what I'm trying to imply is that please take a look at the data provided and find out what is the proportion that is falling outside of the both ends of the specification limit to identify the proportion defect for the case of machine A. Okay, so this one we have a theory we can rely on, which is a normal distribution, but this one is slightly different. So for that reason, we need to know what is the number of items, how many units are falling outside of the both end of the specification limit. So let's find out. Okay, so let's find out. I don't know. So number of COUNTIF in that case in A, the criteria is going to be criteria is going to be less than, right? Less than the lower spec. So it looks like we don't have anything less than the lower spec. Okay, for the what's greater than the upper spec? Okay, range is again greater than. Upper spec here is this guy right here. Sorry, this guy right here. So it looks like also there's nothing falling outside of the upper spec limit. So this has a looks like this process does not generate anything less than the lower and greater than the upper spec. Therefore, it looks like it's generating 0 at this point. Okay. In terms of proportion, you always need to do minus. How many units is here? 250. Okay, so I'm gonna do 2 out of pen. Then 250 here. So the proportion wise, it's 0 here. Okay, so DPMO here is 0. So this is a DPMO, right? Don't worry about this result for now. So assuming the loss function constant is k in here for post process, $, which machine will generate a greater loss? Which machine will generate a greater loss? So we need to find out the variance here, right? We also need to find out the deviation square. Deviation square here. So variance in this case, the variance for this one is always easy. Square of your standard deviation. For this guy, let's just take things that are inside of this parenthesis. You can also do that. We can also do the square too. That will give you the same result. But I'd like to utilize this formula right here. Deviation wise. So this is the this is the mean. The target is 16.9, right? We'd like to square it. Okay, for this guy, the same, right? This guy will be the same, but it looks like this guy has a smaller deviation number overall. Okay, remember when you have this E here, E minus 07 means moving the decimal point 7 position backward. Okay, meaning it's very close to 0. So we now have expected loss here. 8 multiply this and this. Okay, so now we have a full story. By looking at this result, what would you say? So even though this process does not generate any defects by just looking at it, but it will have a greater expected loss. Okay, although it looks like it generates a lot of defects per million, but in terms of expected loss, the process B is going to be smaller. The reason is that the first process, machine A, follows a uniform distribution. Okay, but for the machine B, it follows the normal distribution. Okay, so let's say here is the upper and lower specification limit. um, all of the output are evenly distributed between two specification limits. But here for the machine B, all the outputs are spread across different range, but majority of them are concentrated in this range. Okay, majority of them are concentrated in this range, which are more close to the target. Okay, which are more close to target, but in this case, this is not. So that is the reason why, even though this guy have a smaller DPMO, but it will generate, it will have a greater value in terms of the expected loss in here. So this is what Taguchi loss function is. I think that concludes the question number 4. This is a pretty lengthy, very comprehensive application of what we have learned in chapter 7, and this is the level of the maturity I expect from you to freely navigate between the different measurements that you use to evaluate your system performance. Okay, so I'll stop here. See you in the next video.